Let's try to exemplify this with this example here. So I have a maze, and I'm trying to get from the starting point to the goal point. What are the states, actions, and rewards of this game? What are the states?
So each of the squares is like a state.
Right, so the robot can be here, or it can be here, it can be wherever. Each of these are states of the system. Right. What are the actions that an agent can take?
Going up, down, left, right.
Up, down, left, right, but probably a subset of that because you can't move into the walls. So at every
Right.
state, like the total action space that someone can take is up, down, left, and right. But the actions that are available to an agent at every state is going to be conditioned on the state that they're in. Yes, because we can't move into walls. Okay, what are possible rewards that we can design for this environment? And again, the objective is for the agent to go from the start state to the goal state in fewest number of steps. So how would you design a reward function for this game?
If we hit a wall, then that hitting a wall can be represented as a negative reward. So,
okay, so let's assume that that's a good point. It can be a negative reward. It could cost something. Let's assume that the reward for hitting a wall is negative infinity, so that we never go into a wall. What else? How else would you design your reward? Yes, Mustafa.
Basically, agent goal is to reach on a goal state. So if we calculate the distance between the goal state and the next action he performed, so depending upon the action, if the distance is lesser than before, so we will give positive reward, and if on the other hand we give negative reward.
That's a very good idea. Basically, Mustafa is saying is when our distance is less to the goal by moving into a current state, then I should receive a positive reward. There's only one problem with this, in that the agent has no idea of how far away from the goal they are. That assumes that the agent has global understanding of the game setup. They don't. Like when I'm playing chess, I mean, if I'm really good, I might have a guess as to how many more steps it takes me to win, but that depends on the dynamics of the system, and so I can't be certain of that to receive a reward. But what I can be certain is that every step I take is going to cost me something. It's going to cost me a bit of fuel. Right? So every step I take, let's say that's a -1 reward. When would I get a positive reward? When I reach the goal state. Right? And when I reach the goal state, I'm done. So let's say I get a positive high value number. So let's say that I get -1 per step reward or cost, plus 100 for reaching the goal, and minus infinity for hitting a wall. Okay, so now in this game, as an agent, there are many different policies that I could employ with the hopes of going from the starting point to the end point. One such policy, for instance, is making random moves that are available to me at every point. Randomly aside, up, down, left, right, etc. But that doesn't seem to be like an optimal approach to do so. So just to test your intuition, if I'm in this state here, what is my optimal policy? Sepide, you had the answer, I think.
Yeah, up and down.
So, okay, up and down are that state. What is the best action that I can take, or the optimal policy?
So if there is a wall, I mean, in any direction we can go, right?
Yes. So the action space for the agent in the space that in the state that I've drawn in red is up and down. Which one of those actions is better being in that state?
Oh, I see. So up.
Up, right? Because that, at least based on our understanding of, that's not the agent's understanding, but we know that there exists a policy such that if you're in this state, then up is best. What about this one here? This one obviously is right? And this one here, it's going to be left. Okay. So yes, among the all possibilities of policies that exist, making random moves doesn't seem to be the optimal one. We have an understanding of what the optimal one is because we know the state of the game and we know how, we understand the distance from start to goal, etc. So now we're going to say, how do we go about deriving the optimal policy? That was our goal. How do we go about deriving the optimal policy? By first coming up with a state value function and then deriving the optimal policy from it. Again, state value function or value functions are a measure of the quality of the state that the agent is in, or for the action value function, it's the measure of the quality of the action that an agent can take having been in a given state. So in this example here, we'll see that the state value function will give us something like this. For every state, given the setup that I have for the game, of the states, the actions, the rewards of what we designed on the previous slide, it's going to give me a set of numbers, right? And based on those set of numbers, for every state, now on the right-hand side, I have the optimal actions that the agent can take. And if you look very closely, you'll see that the optimal actions, in a sense, say that if I'm in this state here, I'm going to look at my neighbors, and the optimal action is the one that is the one that increases my value the most. The one that increases my value the most. What I want to plant in your mind is like, oh, an argmax, looking at your neighbors, argmax over actions, where will I land? What will the value be there, right? So all of these are like the iterative things that we'll see shortly. Yes, Juan.
I might have missed this, but where are these numbers coming from?
Where are these numbers come from? We haven't talked about where they come from yet, but they are
Okay.
the value functions over all states, given the procedure that we'll
Okay,
see
got it.
shortly. Remember, we'll go back here. These were the value functions. That was the value function for one state. We just repeat that for all states of the system. What were the states of the system? All of the possible locations of the agent were the states of the system.
Okay.
So through a procedure that we'll see shortly, we'll get these numbers. Once we have that, we can then find the policy that's best for the agent at every state. Other questions? Yes, Mustafa?
Yeah, I have a question here. I just want to know about this thing, as we are cognitive enough to see the maze from third dimension, right? So instead of going left, right, and up and down, we can also see from the top to bottom of the whole graph, right? So is there any way to include this kind of 3D information for the agent while we design this system? So that it can have the better understanding of the graph itself. As we know, the more we increase the dimension over the lower dimension, we have more accessibility to the information, and we can solve the problem, or at least we can understand the problem with larger understanding. So how can we do
that? So maybe to address your question, we have to first ask, what are the information? And then your question is, can we add more information to it? And what we'll see shortly is that, at least within the context of this lecture, where we're talking about model-based reinforcement learning, this means that we assume that the agent actually has a model of the world. And having a model of the world in this context means that the agent has an understanding of all possible states, all possible actions that can be performed in a given state, the transition probabilities that take us from one state to another, and the probabilities thereof, and the reward system that the environment gives us when a particular action is performed in a given state. That itself already is a very, very long list of things that an agent has access to.
But it is also tremendously slow, right? Because you have to consider all possible actions in order to reach them.
Absolutely. But even in this case where the agent has it, it's a very difficult problem. Okay. And commonly in the real world, we'll talk about this in a few minutes. Commonly in the real world, the agent does not have access to some or all of these. And through the process of interacting with the world, it has to discover, well, what is, the state system? What is the action system? What is the transition dynamics? What are the rewards that I get? And then it needs to perform an outer layer of optimization on top of that. So
to wrap it up, like, we have the luxury to be this kind of lavish with kind of problem, right? For example, when we do the pre-training or LLM based of training, we only care about the performance, and okay, we do not look into our hardware cost or compute cost. But if we talk about this kind of problem, even for this maze, we're thinking about few days of computation, right? So
I wouldn't put a number on it, because I guess that depends on the specifics of the problem and the state space size, and also the compute that's available to you. But yes, typically RL problem state spaces are very, very large. Doing a full exploration of the state space and action space and trying to figure out everything in its most optimal manner is intractable for most practical and interesting problems. And so that's where many times we use intermediary models to guide us towards particular states which might have higher probability. Some of the models that are used could be, CNNs or neural networks that we studied before, where the CNNs themselves may be trained on, like you said, a higher level 3D view of what this is.
okay.
And that's kind of along the lines of what AlphaGo did. Basically,
Okay.
AlphaGo had a high-level view of the game chessboard, or the Go board, and they passed that through a convolutional neural net, and that at every stage guided how search happened. That's opening a can of worms that we don't unfortunately have time to go through, but
Yes,
yes,
thank you very much.
I guess the main takeaway is this, and I'll define that formally in a few slides. The agents here need access to an understanding of the states, the actions, the transition probabilities, reward dynamics, and discount factor. Those 5 together are called an MVP. And many times we do not have an MVP. So for today's lecture, we're going to focus on cases where we do, and how would we actually go about finding the optimum policy. And the procedure is what we see on the slide here. Write out and find out the values of every state using the value function. And then either after or at the same time, try to find the optimal policy for that value function. Make sense?
Yes, thank you.
So one final example then for the game of tic-tac-toe. The states here obviously are the positions of X's and O's. The actions are given a particular state of the game. What are the empty cells for an agent to be able to place the X's and O's? The rewards in this case, unless you're super clever about designing a reward function, probably the simplest way is just to say, if an agent wins, they'll get a +1 reward. If they lose, they'll get a -1. And then if it's a tie, then they both get zeros. Policies are, the mapping from states to actions. So pi is the mapping from state to action based on the rules of the game. Where do we place the pieces that we have remaining? And a value function, again, is our understanding, or the agent's understanding, of the quality of each of the states of the game. So the prediction of rewards in future based on the current state. Now, in the game of tic-tac-toe, because the state space is tractable, in this case meaning that there's a finite number of possibilities that you can place these pieces together, and it's actually less than all the possibilities because there are several symmetries that you could exploit, we can use, probability tables to represent the value function. So a probability table like this would give us that for a particular state of the game, what is the probability that the red O player will win? Or in this case, they've already won, so the probability is equal to 1. And so you can write down full probability tables for every state of the game, and that's your value function. And you would use that to then find the optimal policy for the agent.